Okay, I was just asking the kids about the homework and they loved it. And they said the only thing was there wasn't enough. That seems to be the consensus. So, well, I'm going to go around and check homework and you guys are going to fill these. Oh, I'm checking it now. Oh, I'm checking it. You don't want me to check it. I'm going to check it. Okay. So today, what I want you guys to do for the do now, I have these 3 cases here. And for each one, I want you to tell me that, now the red is the actual function, okay? And I've drawn in the tangent line at C. And I want you to tell me what f prime of C is equal to in each case. And also tell me something about the second derivative at C. Now, so I'm looking for like a greater than, a less than, an equal to 0. So just looking at what you have, tell me what the first derivative is, and then tell me if the second derivative is greater than 0, less than 0, or equal to 0 in each of these 3 cases. You got it? Pause time. We're back. We're back. All right, guys. Now look at this first case. What can you tell me about f prime of C? What does it equal? 0. Does everyone see that? So the slope of the tangent at C would be 0. Awesome. Now, the second derivative at C, would you say that's less than 0, greater than 0, or equal to 0? Less than. How did you know that? Concave down. I like it. Woohoo! All right, case 2. We got our little graph here. What about the first derivative at C? 0 again, because that's just the slope of the tangent, the first derivative. What about the second derivative at C? Greater than 0. See, it's positive because it's concave up the function, so the second derivative is positive. And third case, what about the first derivative at C? 0. What about the second derivative? Equal to 0. Just said 0. F double prime of C, 0, 0. Okay, now, I'm going to go over the homework, but this is such a short lesson today. Before I break away, while we're kind of looking at this, I want to just get into how we can use this. You know, like how we find extrema. We get the first derivative. We find our critical values. We make a sign chart, right? And if the sign changes, we've got a max or min, right? That's the first derivative test for extrema, and it's lovely. I mean, but sometimes you just want a little change, right? You want another way to do something. You get sick of the old way. And this is a fun, quick little way to find extrema. This is called a second, yes, it's easier. It's called a second derivative test for extrema. It works particularly well with polynomials, where you don't have derivatives that look like fractions, you know? Yeah. And basically it works like this. You find the first derivative and see where it's 0, okay? Which is the case in each one here. Because that tells you where you have a horizontal tangent. So you find out where the first derivative is 0. Let's say it's 0 at 3. And you plug 3 into the second derivative, and you get a negative number. What do you think that tells you about the function at 3? It's concave down there, and since you had a horizontal tangent, you have a max or min. You'd have a max. It'd be like the first case. So if you find out where the derivative is 0, take that number, I have a C here, but it could be 3 or whatever number, and you put that into the second derivative, and you get a negative value, you know you got a max there. You don't need a little sign chart. If you take, what's that? Correct. Yeah, that would be the information you get from that. Now, if you get that first derivative, you set it equal to 0, and you pop that number into the second derivative, and you get a positive value, that means the graph's concave up there. So what do you got? You have a min. Now, I love this test, like to find extrema. It's great because it's quick. The only thing is, if you get 0, you set your first derivative equal to 0, you get a value, you throw it into the second derivative, and you get 0, you don't get a positive or negative, then you have to do, it's inconclusive. You got to go back and do your whole first derivative test. If, like, let's say you set the derivative equal to 0. I'll show, let me give you a little example of that. Let's say you have a function, this is the classic, x to the fourth, okay? You get the derivative, 4x to the third. You set it equal to 0, because that's where you can have your horizontal tangents. And what do you get? All right, you get 0. Now, if you take 0 and you put it into the second derivative, first of all, what is the second derivative? 12x squared. If you plug 0 into the second derivative, you get 0. You don't get a positive or a negative. Well, it could be, a point of, you don't know. It's inconclusive. Does anybody know what the graph y equals x to the fourth looks like? Normally, to the fourth power, they do, but it actually just looks kind of like a parabola. It's not a parabola, but it's fat in the middle and just goes up like that. And at 0, there really is a min. But we wouldn't get that from the second derivative test. That's the only time this fails, is when you set the derivative equal to 0, you take that number, you put it into the second derivative, and you get 0, then you have to do a sign chart for the first derivative. No, you don't know that. You'd have to do the, it's really changing sign. All right, but, yes. Yeah. But it really is a great little technique, and we're going to do a few examples of those. Should we do them first? Because there's only like 2 of them. No, let's just do it first, and then we'll go over homework. Is that all right? Because we're like in the flow right now. No, the homework was so much fun. Wait, we're not going to do that yet. We're going back, though, because I want to show you. Yep, I didn't see it. Oh, went way too fast. Oh, no. Yeah. This is it. This is the first one you have, right, guys? Now, if they just said find the relative extrema, you could use whatever you want to find where it has a max or min. But they actually say using the second derivative test. So what's the first thing you got to do, kids? Get the first derivative. So write down what the first derivative is. We can all do that. Now, what do we got to do next? Okay, but before we get the second derivative, actually, I want to find out where this is 0. Let's just set it equal to 0. I mean, it doesn't matter the order we do it in. So I'm finding out where I have my horizontal tangents. How do we solve that? Yeah, I want an answer. We got both 2 and -2? Or did you do like the x plus 2, x minus? You don't even have to do that, right? If you like the dots, you do the dots. Yeah, plus or minus the square root. As long as you don't forget, that's good. Okay, so now we know that we have a horizontal tangent at each of these places, but we don't know if we have a max or min. So now we got to get the second derivative. Second derivative is 6x. And let's first check out that -2. If we put -2 into the second derivative, do we get a positive or a negative? Yeah, we get a negative number, right? Like it is -12, but we don't care what it is, right? It's negative, and if the second derivative is negative, what does it mean about the concavity? Right. All right. I'm not even going to write -12. I'm just going to go like this. So do we have a max or a min? Yeah. So we have a max at x equals -2. Isn't that fun? Okay, let's find out like what was going on at 2, because at 2, the derivative was equal to 0. So let's plug 2 into the second derivative. Is that going to be positive or negative? Positive, right? And that means that it's concave up. So what do we have at 2? Min. So we have a min right? I love this test. This is a test I always use. The only time it's annoying, like, when you have uh, fractions and all that. No, but for polynomials, it's the best. Okay, let's try another one. This time, I'll let you guys try the next one first. Oops. Hi, Simone. What are you doing? She likes that. No. I'm, yeah. So you pull out 4x, right? And what goes in here? Good. Now, you can factor that again with the dots, the x squared minus 1, or you could just know, you set this equal to 0. You want me to factor this again or just write x equals? Okay, you can handle that, right? You just don't want to forget the negative 1. So there are 3 values of x where the derivative is 0. We got to plug each of these into the second derivative. So what is the second derivative? Where am I going with this? I have no room. Yeah, I got to move all this over. I didn't plan my space. Oh. This is the exciting part of the video. Okay. All right, so I'm sorry. So the second derivative is, you said 12x squared. Is that it? Uh-huh. Okay, so we're going to plug in the negative 1. Do we get a positive or a negative? Positive, right? Like, we actually get 8. That's positive. So what does that mean? Yeah, I shouldn't have drawn that. I did that too quickly. All right, sorry about that. Well, the next one. How about the 0? We plug 0 in. Yeah, we get a negative. It doesn't matter what it is. The fact it's negative, it's concave down. So what do we got there? Max. And then, so I really should say a min at x equals negative 1. We've got a max at x equals 0. And we got to just do the 1. We plug 1 in, what do we get? 8. That's positive. I mean, we don't even... And if it's positive, it's concave up. So we got a min at x equals... Yeah, right? It's my favorite way to get the extrema. So nice. So basically, when Simone comes back and she says, hey, how do you use the second derivative test to find extrema? What's the first thing first thing she should do? Okay, so she's going to find the first derivative, and what are you going to do with that first derivative? Set it equal to 0. And set it equal to 0. I don't know why I wrote it like that. That's just bad. Oh, well. All right, and then you solve it, right? Solve. And then what do you do? Yeah. Plug each of those solutions into the second derivative. As a special effect. I don't know what that was. Of the solutions into the second derivative. All right, and we know if you get a positive, it's a min, a negative, it's a max, but if you get 0 inconclusive, you got to go back and do your first derivative whole sign chart thing. The one that I was telling you about, I just have it here so you can see it. What do I have here? Yeah, like that one. If you did, like this is the one we were talking about before. So just once again, if you get your first derivative, you solve it, you plug it into the second derivative, and you get 0 inconclusive, you got to go back and do your first derivative. You make your whole sign chart, mark it off at 0, and take test values on either side to know what you have there. That's the only thing that's not the best about it. Okay, ready to talk about that homework? Yeah, no way. But I think that there's some cool ones. I was sorry to see how 19 went, but before we get to 19, Yeah, I went way too far. What questions do you have on it, on the homework? And I'm fine with talking about 19 too. But is there anything before 19? Yes. 17. X to the 1/3, x minus 4. And the directions for 17 find all points of inflection. So all we care about is the second derivative, okay? Making a sign chart for it and see if it changes sign. That's our goal. So we got to get the first derivative. What do we got to use? Product rule. First, unless you wanted to distribute first. Okay, so we'll do it like that though. First, derivative of the second, 1, plus the second, times derivative of the first. What's that going to be? Oh yeah, because it's x. You guys are good. Because it's x to the negative 2/3, so you're going to have a cube root of x. You know what? I'm going to write it as x to the negative 2/3 for here for a second. X to the negative. Oh, one. I erased that. Darn. All right. Try it one more time. 1/3 x to the negative 2. Okay, that's the first derivative. Now, I'm almost wondering if we should distribute first and then take the second derivative. Yeah? All right, let's try that. I don't know how bad this is going to get. Oh, nice. If we distribute, we multiply this by the x. What happens when you multiply 1/3 x to the negative 2/3 times x to the first? What do you get? You add the exponents, so we can get 1/3 x to the, ooh, that's fun. You see that? If we multiply x to the first times 1/3 x negative 2/3, you get 1/3 x to the 1/3 because you got to add exponents. And then we got to multiply by the negative 4, so we'll have negative 4/3 x to the negative 2/3. Okay. Now, before I take the second derivative, it's always good to clean this one up. We've got some like terms here. We have a whole x to the 1/3. We've got 1 x to the third. Okay, you guys see that? If you have 1 x to the third plus a third x to the third, you get 4/3 x to the 1/3. Who didn't like this? So we have 4/3 x to the third minus 4/3 x to the negative 2/3. I'm thinking about factoring out that 4/3. Why not, right? So we have 4/3 x to the 1/3 minus x to the negative 2/3. Okay, so this is our first derivative. That's kind of, if you like thirds, it's the best. All right, let's get the second derivative. When you have a constant multiplier and you go to take a derivative, what do you do with that constant multiplier? Just drop it down. Drop it like it's hot. So we leave that. Now we're going to multiply by the derivative of the x to the third minus x to the negative 2/3. What's the derivative of x to the 1/3? Good. Okay, now the derivative of the next term. Well, first we just plus 2/3, yep. X to the negative 5/3. Okay. Now, we have to find out where it's 0 and defined, so we got to rewrite this. I'm thinking, well, that 4/3 we're just going to leave out because that's not going to affect where it's 0 and defined. Well, I'm going to leave it there, but I think with this, I want to rewrite them as fractions because with these negative exponents, so you got to do. So 1 over, this would be 3 times the cube root of x squared. What is the next one? Okay, right. So we have 2. Oh boy, that could, okay. Oh boy. Cube root of x to the 5th. Yeah, because we want a common denominator, but it really wouldn't be ugly if we broke this up. Can anyone stay with me and not run away at this point? Does anyone say, like, because the cube root of x to the cube root of x to the 5th, can we break that up? Wait, this was your question, so I'm going for it. Yep. This can be broken down because x to the 5th is x cubed times x squared. Cool. I could hear the kids saying that. Cool. I just repeated that because you can't hear it. So we're going to write this as 2 over 3x times the cube root of x squared. And the reason that is so cool is because we need a common denominator. We need to put them together. So the common denominator would be this denominator, the 3x times the cube root of x squared. You see that? So for this first one, this first fraction, what are we going to multiply top and bottom by? X, right? We'll just multiply this one by x over x, and now we'll have the same denominator and combine them. So we have 4/3. We're going to have x plus 2 in the numerator, and then 3 times the cube, 3x, excuse me, 3x times the cube root of x squared. All right, here's our second derivative. Now, what values of x make the second derivative equal 0? Yes, down. -2. So the second derivative equals 0 when the numerator is 0, so when x equals -2. What value or values of x make it undefined? What value of x makes the denominator 0? Denominator equals 0. There's only one value of x, 0. So we have 2 possibilities for where we could have a point of inflection. So we make a little second derivative sign chart, mark it off at -2 and 0. This ought to be good. All right, give me a value greater than 0. I like 1. I wanted something that was like a perfect cube, so I don't know, I'm not calling it f double prime now, but 1. 4/3 always positive. How about the x plus 2, the numerator? If x is 1, x plus 2 is positive. How about the denominator? Positive or negative if x is 1? Positive. Everybody's positive. Hooray. Okay, let's take a value of x between -2 and 0. -1. All right. Let's just focus on what now. We have the 4/3 out front. That's positive. How about the x plus 2? If x is -1, numerator is -1 plus 2. Yeah, okay, so it's positive, right? This is what we're doing, little steps. Now, if x is -1, we have 3x out front, which is negative, but then we're multiplying it by the cube root of -1 squared. Cube root of -1 squared, is that positive or negative? Cube root of -1 squared. Positive. So we have a positive over a negative times a positive. So it's negative. You could get hurt doing a problem like this. You could get hurt. Yeah. All right, let's take a number less than -2. That's a perfect cube. So I have to take the cube. Yeah, -8. That's what I was thinking. Fine. All right. Nice. All right. Just want to think about the little pieces. So if x is -8, 4/3, we don't care about that. That's positive. The numerator, x plus 2, is that positive or negative? Negative. Then we have the 3 times the -8 out front. That's negative. And then we got to multiply it by the cube root of -8 squared. Cube root of -8 squared. positive. So we have a negative over a negative times a positive. So it's a negative over a negative, which is positive. Oh my gosh. Now, are both of these values in the domain before I just go and say, okay, we have a point of inflection at -2 and 0, because you can't have a point of inflection if it's not on the graph. I just want to make sure, because I forgot what the graph looked like, what the actual function was. Where was that actual function? That was a long time ago. But yeah, no, they're both in the domain. Okay, so we have points of inflection at both of those. So we have a point of inflection at x equals -2. Well, I was going to say a point of inflection at x equals -2 and at x equals 0. Oh my goodness. Good one. No? And then you want to like put it in your calculator and graph it. We have time to know another one. Yeah. Number 11. I'm glad you asked that one. That was the piecewise, right? Okay. You just skipped it. Okay, so 11, it's this function, it's a line when x is less than 1. It's this line with a slope of 2 for x values less than 1. And then it's a parabola when x is greater than or equal to 1. This is our function. And in number 11, what are we trying to find? Is that the one we have to find everything? I hate those. I mean, I love those. Oh, no, they only cared about concavity for 11. You guys got off easier in this. Okay. So to get the first of all, it's not even continuous at 1, because if you plug in 1 into the top branch, you get 2, and then into the second branch, you get 1. So at 1, it's not continuous. Not that that really matters, but it's not, the derivative doesn't exist there. But you take the derivative of the top branch, you get 2. Derivative of 2x is 2. The derivative of 2 minus x squared is -2x. So the derivative, the slope is 2 when x is less than 1, and -2x when x is greater than 1. Now, but we got to get the second derivative, because it asks us about concavity. So you got to take the derivative of 2, which is 0. So the second derivative is 0 when x is less than 1, and it's -2 when x is greater than 1. So as far as where is it concave up, well, this second derivative is never positive, so it's never going to be concave up. Where is it concave down? Well, the second derivative is negative when x is greater than 1. Point of inflection would have to be where it changes from positive to negative or vice versa. It doesn't. It's just concave down from 1 to infinity. And if you think about what the graph looks like, I hope that makes sense, because your graph, it's just a straight line until it gets up to x is 1. Right? It's not concave up or down there. And then it's part of this parabola when x is greater than 1. It's just concave down. So it's concave down from 1 to infinity. It's never concave up. No point of inflection. I know the piecewise scared you, but I wanted to, can I just show you something really cool with 19? Can I, like, just like 1 second? You don't even have to like really pay attention, but just, I thought it was kind of neat. We got into it another period. This one was actually cool. Like, this could make you go crazy, right? We had to find the points of inflection in 19. We got our first derivative using the quotient rule. Then we had to distribute. Where did it go? Okay, and like combine like terms. That's what all these colors are. You can look at this at home and like play it really slowly and really get into it if you want. But yeah, you had to distribute the x minus 2 over this trinomial there. Combine like terms. So you get your first derivative and you think, okay, good. Now I'm ready to get my second derivative. So you get the derivative of that using quotient rule again, right? This was so bad. So we did the second derivative. We used the quotient rule. We had to distribute again, trying to, before you can see where it's 0 and define. And we got to, and trust me, this is just a bad thing here. We had to distribute. Well, because you had to multiply it all out before you can see where it's zero and defined. Yeah, I felt a little bad about this one. But then, guys, after you combine all the like terms, you get to this point. Then this, yeah, like how do you even factor that? So you just got to guess possible rational solutions. And I did a little synthetic division over here on the side and said, oh yeah, 1 is a 0. And so then, so we can factor this again. Yeah. Well, no, we use the answer to get that. But, because I was like, wait, really? It is a 0. But then this other factor, this quadratic factor, has no real zeros because the discriminant is negative, b squared minus 4ac. So it has these two critical values, right, at 1 and 2. And you make your sign chart, and you see that it changes sign at 1 and 2. But here's the kicker. 2 is not a point of inflection because it's not in the domain of the original graph. It's not even, like, if you look at the original function, and can I just show you this one thing? This was really neat. So I put it in the calculator to see what 19 would look like. Because with all that work, you found out that the point of inflection was at 1. This was your point of inflection right here. 2 was not in the domain, so you can't say that because there's an asymptote at 2. Well, the cavity's changing here. It's going from concave down to concave up. Okay, so but it has to be a point on the graph to be a point of inflection. Yeah, 2 was not in the domain. Oh, that was fun. Yes. All right. Tonight's homework for number 4, just make a sign chart for the first and second derivative. You'll see it. Oh, good.
So just like that?
Yeah. Yeah. That's exactly what we have to do. Let me turn this thing off. Yeah, for that number 4, you make a sign chart. Yeah, it is a weird question. Aw, don't make him run. He's got to get over this.